Assalamualaikum guys. So we'll continue our chapter 5 with a complex power. Okay. So what is complex power? Complex power is actually a parent's power in uh, a complex forms, right? So complex power, they say that here complex power S is the product of the voltage and the complex conjugate of the currents, right? So usually complex power is denoted by the bold S over here. This is our complex power. Okay, so it's quite similar with the uh, our uh, our study previously, which is our load as a complex load or admittance and also impedance, right? We are using a complex form in order uh, to to do the analysis for our circuit, right? So as you show from the uh, as as the as shown in the figure. Okay, so you have a load over there, Z load, and then you have a voltage across that load and also the current I. Okay, that through the load. So therefore from there we know that V, this is actually our V in a passive form. V equal to V max with the degree of theta V, and then your I is equal to I max with the degree of theta I. So therefore complex power can be write as a 1 over 2 V I conjugate over here, right? So this is what we call it as a complex conjugate of the current. Okay, so and then we also can write your complex power S by using RMS value, which is complex conjugate is given by VRMS IRMS with the degree of theta B minus theta I. Alright. So here, okay, so from here, okay, we can elaborate more. Okay, we can elaborate into a complex number, which is your power S. Okay, can be write as equal to in a complex form. Actually your S equal to P plus JQ, which is P actually is your average power in watt, right? So and then given by this equation, which is VRMS IRMS cos theta V minus theta I, and also your Q is actually your reactive power. Okay, so reactive power is given by VRMS IRMS sin theta V minus theta I, right? So therefore our complex number is actually consists of your average power in watt and also reactive power in VAR unit, right? So therefore complex power can be write as S, right? Remember the bold S equal to P plus JQ. So P is an average power or real power, and then Q is our reactive power, which is the power at our reactive part. Okay, so therefore the unit for P is in watt usually, and then the unit for Q usually we got from VAR. Right, so let's say if your Q part your is equal to 0, then we know that your uh, load is actually a resistive load, right? So and then usually the power factor will become will equal to 1. And then let's say if your Q is less than 0, right? So your Q part here is less than 0, we know that your load is actually a capacitive load. Okay, and then capacitive load usually give a leading power factor, right? And then when your Q is larger than 0, okay, so we know that Q larger than 0 usually is an inductive load, right? So that's mean if your part here when larger than 0, we know that is a positive, right? So if you got P plus positive JQ, we know it's an inductive load, and then usually inductive load lead for the lagging power factor. And then let's say if your S equal to P plus J minus JQ, okay, minus, we know that is Q less than 0. We know that your load is actually a capacity loop and lead for the leading power factor. Okay, so one more. Okay, this is I already show, I already tell you, which is S equal to V RMS IRMS cos theta V minus theta I plus J V RMS I RMS sin theta V minus theta I, which is this part is actually your average power, and then this part is actually your reactive power. So S is actually our apparent power and given by VRMS times IRMS, or you also can write your apparent power by using our power triangular, right? So if you have a, remember the power triangular, so this is your theta, this is your P, this is your Q, right? So this is our S. So therefore you can get the value of S over here by using a theorem Pythagoras, which is P squared plus Q squared, Z P squared plus Q2 squared, right? So and the real power is the P part over here, is given by the S cos theta V minus theta I, which is cos theta V minus theta I is actually P over S, right? So therefore P equal to S cos theta V minus theta I. And then reactive power, which is our imaginary part over here, is given by S sin theta V minus theta I, right? So and then lastly we have a power factor. Power factor over here is given by P over S, right? P over S is actually cos theta V minus theta I. Okay, this is a diagram, power triangle diagram. If you see the first one is actually power diagram for inductive load. From what I told you, if your Q is larger than 0, we know that actually your load is an inductive load, right? And then if you have your Q less than 0, okay, therefore we know that our diagram is a capacitive load. So for inductive load, remember inductive load usually you have a lagging power factor, and for capacitive load you have a leading power factor, right? And then the same thing, you can see here, you can represent our complex power in a form of power triangle over here. Essentially this is a type of power triangle. You also have a impedance triangle over here, and then power factor. This diagram actually show you a power factor indicate in a you know actually when your Q is positive, we know it is a lagging power factor, and then when your Q is negative, right, so it's a leading power factor. So usually leading power factor is your capacitive load, and then lagging power factor is your inductive load. Okay, so this is another things you need to consider when we consider the total power, apparent power, the total reactive power, and also the total apparent power. Alright. So okay, the total number of watt, if you say watt, we know that this is actually our active or real power, okay, which is P, and then you have volt ampere reactive, VAR is actually power for reactive power, and then you have volt ampere. Volt ampere usually our apparent power, and the power factor of any system can be found using the following procedure. This is a power factor. This is a way when we want to find a total uh, uh, total real power and total reactive power, and then the total apparent power, and also the total power factor for the system. So this is the step that you need to consider, which is the first one. You need to find the real power and reactive power for each branch of the circuit. Okay, when we say real power, remember is P, and then reactive power is Q. So you need to find this P and Q for each branch of the circuit. And then next you need to the total real power of the system, right? Total power, PT, is the sum of the average power delivered to the each branch, right? So this is the total power. So the total power is consider your total average power or real power. So the total reactive power, QT, is a difference between the reactive power of the inductive load that of the capacitive load. So in order to find the total reactive power, you need to find the difference between the reactive power and also reactive power of the inductive load and also the capacitive load, right? So, and then the last one, in order to find the total apparent power, which is ST. So ST, actually we are using a theorem Pythagoras, which is PT squared, assert PT squared plus QT squared equal to our apparent power. And then last one, in order to find the total power factor, so total power factor is, we can use this PT divided by ST, right? So one again, okay, this power triangle is very important. This is P, this is Q, this is S. Power factor is cos theta, so that's why you got cos theta is actually P divided by S. Okay, in this case we are looking for total power factor, so that's why PT divided by ST. Okay, we go for one example. For this one, let's say you need to find the total of what volt ampere, which is, you need to find the P total, right? And then you need to find the Q total over here. Volt ampere reactive is a Q, reactive power, and then volt ampere is your S total, right? And the power factor of the network in the following figure. This is the figure, right? Okay, and then lastly you need to draw the power triangle and find the current in Passer form. Okay, so first thing, we need to find the P of T, Q of T, and N of S of T, and also total power factor. After that, we need to draw the power triangle and also need to find the current in a Passer form, right? So this is the circuit. You have three load, which is load 1, load 2, and load 3. So in order to find PT, QT, and ST, remember this step. Okay, to find the real power, total real power, you need to sum of the average power delivered to each branch. And then for reactive power, you need to consider the difference between reactive power and reactive power of the inductive load and also the capacitive load. And then after that, after we can find the PT and QT, so we can find the total apparent power, and then from there we can find the power factor. Right, from here, if you see load 1, say we know that at load 1 you have 0 VAR and 100 watt, so we know that this is our P1, consider. Alright, and then because they know the value of VAR is 0, we know this is not a reactive load, right? That means it's not a is not consist of inductor or capacitor. It might be a total resistant load. And then you see load 2, you have 700 VAR and then 200 watt. Okay, from here we know that this load consists of resistor and also inductor is given over here, and then the value is 700 VAR for Q, and then for P you have 200 watt, and then load 3 over here is given by 1500 VAR capacitive load and also 300 watt for resistive load. So therefore from there, in order to find your P total, we know that P total, we just use the summation of the P, which is you can find P total by P1 plus P2 plus P3. Okay, this is considered P3, right? P2, sorry, this is considered P3. So therefore, P total is actually 100 plus 200 plus 300, which is equal to 600 watt. So total number of watt is actually equal to 600 watt. And then next we need to find the QT. QT is a total reactive power. So if you see load 1, you don't have any reactive power. Load 2, we have an inductor, and then load 3, we have a capacitor. In order to find the reactive power over here, okay, the total reactive power is the difference between reactive power of the inductive load and that of the capacitive load. We need to find the difference between reactive power of the inductive and also capacitive load. Okay, so we just compare the 700 VAR and 1500 VAR over here. So the value of capacitive load is higher compared to the value of inductive load. So a comparison, that means we need to subtract these two value. So if you subtract this for 1500 700, so QT is actually equal to 100 VAR. Okay, which is from here we know that because we deduct inductor from the capacitor value, so the capacitor value is higher, so it's still in a capacitive load, right? So QT equal to 100 VAR, 800 VAR, right? And then last one, we need to find the volt ampere. All right, volt ampere is given by this one, apparent power ST. Okay, so therefore ST is actually PT squared plus QT squared, set of it. So therefore 600 plus 800, set of it. So therefore the value of this one is actually equal to equal to 1000 volt ampere, right? So this is the total apparent power. And then last one, power factor is given by, power factor is cos theta V minus theta I. So from here power factor is PTST. Alright, PT divided by ST. Alright, so therefore PT is 600, ST is 1000. So therefore 6 divided by 10, so is equal to 0.6 Okay, and then because we know that our reactive power is a capacitive load, so therefore your power factor is actually a cap, cap is a capacitive load, right? 0.6 with a capacitive load or leading. We can say that power factor is leading. Sorry, we have it here all right. So this is a 0.6 leading capacitor, right? And then last one, okay, you need also to draw the power triangle and find the current in passive form. So therefore, with all those value, we can draw our power triangle. We know that our power triangle is our load is a capacity load. So therefore, uh, our power triangle is like this because our QT is capacitive. So therefore, you got downwards Q, and then this is your ST, and then this is your P of T, right? So therefore, from here we can find the theta value. Okay, theta value is get from, because power factor is 0.6, so therefore cos theta equal to 0.6. Theta is actually cos 0 cos arc cos 0.6, which is theta equal to 53.13. Okay, so next we want to find the current. So the current can be found using this formula, right? Which is power, apparent power is given by VI. Okay, apparent power is equal to total apparent power is equal 1000 volt ampere. Okay, therefore from here we can find I, which is I equal to ST divided by V, which is V is 1000 volt ST is 1000 volt ampere, and your V volt is given, I think volt is given here 100, right? So therefore divided by 100, I equal to 10 ampere, right? So therefore in a passive form, I equal to 10 ampere with a degree of 53.13 degree. Okay, so I think that's all for a complex power. So we stop here.